Hello everyone, welcome back to the next video on reinforcement learning. In this video, we'll be talking about the different elements for a reinforcement learning agent. So before we get started with the material, following are some acknowledgements. The slides are based on a video lecture series by Professor David Silver and chapter 1 of the reference book Reinforcement Learning by Sutton and Bartow. Okay. So, when we talk about the elements of reinforcement learning, the first thing that we talk about is the reward signal, which is something very unique to reinforcement learning. So, a reward function or a reward signal is a measure of how well the agent is doing and can be thought of as like a feedback signal. So, typically, the reward function or the reward signal is a scalar value. So it's a single number which defines how good or how bad the current action of the agent is. So all of reinforcement learning algorithms are based on this idea of a reward hypothesis. So what we mean by the reward hypothesis is that all goals that can be achieved by an agent can be achieved through the maximization of the expected cumulative reward. So what we mean by this is the rewards that an agent can receive can be stochastic. So what that means is if we are in the same state and if we take the same action, sometimes the agent might receive a very good positive reward and sometimes it might receive a negative reward. So what we want to do under this reward hypothesis is that the goals can be achieved by maximizing the expected cumulative reward, which is the average reward that the agent receives. So what we are saying here is quite a bold statement, right? So I just want all of you to think for a while if this really makes sense, right? Do you all agree with this statement? So the first time I heard this statement, I felt it was a very big statement, right? And for me, the main confusion was that um, if I consider myself as an agent, as a faculty here in the college, so I have multiple goals that I'm simultaneously maximizing, right? So sometimes maybe I'm mentoring students for their major project, or sometimes I'm teaching classes, right? So, and each of those goals have different rewards and different expectations. So, my concern was that is a single scalar signal sufficient to maximize all goals, right? And the answer for this is that it is still sufficient because at any point of time, I'm only trying to achieve one goal, right? So either I am mentoring students or I am preparing for a class or teaching a class. And if the time becomes granular enough, at any point of time, I'm only achieving one of the goals, and a reward function can be defined to achieve that particular goal. And by this extension, a composite reward function can be defined, which can try to address each of these goals. And at any point of time, one component of the reward function can give reward for the current goal that I'm trying to achieve. So the reward hypothesis does hold true, and all goals can be achieved by maximizing the expected reward. So let's look at some examples of a reward function. So if we are talking about a self-driving car, right? So we can define positive rewards if the car is driving safely, and we can define negative rewards if the car is driving off the road and then colliding with some objects. Now, if we look at robot locomotion, right? So this cartoon image that we see over here is the Atlas robot, which is designed by the Boston Dynamics company. So you might have seen on YouTube where this robot is doing a lot of acrobats and can run around in natural environments, right? So if we want to design an RL algorithm which can make this robot walk, then we can define a reward function where we can give positive rewards as long as the robot keeps moving forward, and we can give negative rewards if the robot is losing its balance or it falls down, right? So these are some examples. Now, here are some more examples, right? So let's say we have a power plant, right? A thermal power plant or a solar power plant, and we want to maximize the energy that is generated by this power plant. Then we can assign a positive reward as long as the power plant is generating power and meeting its demand, and we can assign a negative reward if the either if the power plant is generating too much power and making it dangerous, or it's supplying too less power and there is no power supplied to the end users, right? So this is how we can define a reward function for power plant optimization. On the other hand, if we are talking about the investment management or portfolio management, the reward function is quite straightforward. So the agent gets a positive reward if the net worth increases, and the agent gets a negative reward if its net worth reduces. So these are some examples, right? Now that we have looked into what the reward is, let's look at the actions, right? So how we can define an action is the decision that an agent takes at each time step, and we can define it by AT. And what this action actually does is it goes as input to the environment, and based on the action, the environment actually generates the next state and the next reward, right? So again, if we are talking about the example of stock manage or portfolio management, the actions that an agent can take can be considered as discrete actions, right? So the agent can choose to buy two stocks of or two units of stock like Tata, or it can choose to sell three stocks of some other company, right? So the agent always has some discrete actions where it's either buying 2 units, 3 units, or sell 3 units or 5 units, and so on. So whenever we have these discrete actions, it's possible to use traditional RL algorithms, especially something called value-based algorithms, which is the focus of this reinforcement learning course. On the other hand, an agent can also have continuous actions, right? So if we take the example of a robot which is navigating in an environment, the robot has some motors available in each joint, right? So controlling this robot is actually trying to send some signal to each of these motors so that it applies a certain joint torque, right? So these joint torques that the robot can apply are continuous values. So you can apply a torque of 2.3 Newton meters or 5.6 Newton meters and so on. Now, wherever continuous actions come in, instead of traditional RL algorithms, we might need to use some form of approximation, right? Function approximation. And we don't actually solve for every possible action. And we end up deriving an approximate solution for solving the task. These are some of the more advanced types of reinforcement learning algorithms. And this domain of deep reinforcement learning, where the function approximation is done using a neural network, is one subset of RL algorithms. Okay, so now that we have looked at actions, let's look at the states, right? So what we looked at some of the previous videos was this definition of a state. But before we talk about the state itself, I think it's important to talk about the observation, right? So observation is actually what the agent can see in the environment, right? And there is a difference between state and observation. So if we look at the example of a self-driving car, right? So the actual state of the environment is where every object is in the environment, like let's say there could be a butterfly flying on the road, or there is like a specific amount of wind flowing on the road, and then the exact amount of friction between the tire and the road. And the state can actually include a lot of information about the road and the environment. But what the agent actually observes is, let's say if the self-driving car has certain cameras, then with each camera, the agent can see certain parts of the environment. And then based on the reading that it gets from the speedometer, it can have some estimate of its current speed, right? So what the agent actually observes can be quite different and much less information compared to the actual state of the environment. So now when we are looking at an observation, at each time step t, the agent receives some observation OT and some reward RT, and then based on this, the agent takes some action AT. Now the environment, on the other hand, takes this action AT as an input, and then it updates the environment state, and then in the next time step it outputs some reward and some observation OT, right? And again, as mentioned before, the time t increments when the environment updates the state and reward. Now that we have defined this concept of an observation, we can define the concept of history. So let us say the agent is interacting with the environment in one episode, right? So for that episode, the history is defined by the sequence of observations, actions, and rewards. Now, given that this is the current history provided to the agent, what happens next actually depends on this history, right? So the agent actually executed a set of actions and has this history. So based on this, the agent selects the next action, and then the environment reacts by giving the next reward and the next observation. So the state which we defined in the previous videos is actually some information that is derived from the entire history that the agent sees, right? So in some scenarios, we can only choose to look at the current state, or in some scenarios, we might choose to look at the entire history to define the current state, right? So now that we have defined the observation, there are different types of states that we can define, right? So the first one is something called the environment state, right? So in the environment state, this is the actual state of the environment, and this is what the environment actually knows about itself, right? So that is why I have given this representation in the environment, right? So this is actually the data that the environment uses to pick the next observation and the next reward. So in most of the cases, the entire environment state may not be visible to the agent. So if you again go back to the self-driving car example, there may not be enough sensors placed on the car so that the car can observe or know everything about the environment. Now, there is something else which is called the agent state, right? So we can think of this as the internal representation of the state that the agent has. So this state that an agent uses is basically the information that the agent has to pick its next action. So this could be very different from how the environment behaves, right? And again, the agent state can be some function of the entire history, right? So in one of the previous videos, we have seen the use case of Atari video games, right? So in that particular example, the agent uses the previous 4 observations as the state representation. And maybe a different robotics application might use more information of the history to define its next action. So to give a more concrete example of what the agent state is, let's look at this example, right? So let us say we place a rat inside a environment, right? In some sort of a cage, and that cage has a light which can go on and off, and it has some lever which the rat can pull, and then there is some bell that can be rung, right? So in the first episode, um, where the rat interacts in this cage, it saw the light glow up once and then light glow up again. And then the rat pulled the lever and then there was some ringing sound and then the rat got electrocuted, right? In the next example, in the second episode, there is some bell that is rung and then there is the light that comes on and then the rat pulls the lever twice. So after doing this, the rat received some food as an output. So you can think of this as negative reward and you can think of this as positive reward. So in episode 1, the rat received a negative reward, and in episode 2, the rat received a positive reward, right? So now let us say the rat is going to episode 3, right? And then it pulled the lever once, it got the light, it pulled the lever again, and it got a bell. Now, if the rat were to anticipate whether it will get a positive reward or a negative reward, it really depends on what state the agent chooses, right? Or what state representation the rat has. Now, if the rat chooses to look at the last 3 items in the sequence, then the last 3 items in the sequence is bell, lever, and light. And here it is light and 2 levers. So because there is a match between episode 1 and episode 3, if we look at the last 3 items, the rat can expect a negative reward, right? So based on this, it can expect a negative reward. Now, if the rat is just counting the number of bells, levers, and light, then the count actually matches with episode 2. So episode 2 has 1 bell, 1 light, and then 2 levers, right? And episode 3 also has 2 levers, 1 light, and 1 bell. So if it chooses to have this as a state representation, then the rat can expect positive reward, right? But if the rat is just remembering the entire sequence, right? Like, oh, the first episode was 2 lights, lever, and then bell, then actually episode 3 does not match with any of the episodes. So the rat cannot expect either a positive reward or a negative reward. So what this example shows is the internal representation that an agent has can decide which action that the agent takes and can also give an anticipation of what reward the agent can expect. So now that we have defined like the environment state and the agent state, there is something else called the information state or the Markov state. Now, the information state or the Markov state contains all the useful information of the history, right? And we can define it as a Markov state only if, let us say, we are trying to define a probability distribution which says what is the probability that we go to state st plus 1, right? Given that the entire sequence is S0, S1, so on until St. So if we are trying to model this probability distribution, and if these can be replaced by this, where the probability of the next state only depends on the current state St, and we can ignore the entire history, then it's called a Markov state. So what this means is the future, which is this sequence that we will see in the future, is completely independent of the past, which is the sequence of observations received from time 1 to t, given that we have the Markov state St. So this St makes it independent from the entire history. So what we can say is that we can consider the Markov state as a sufficient statistic of the future. So what we mean by a sufficient statistic is, if we think about a Gaussian distribution can have a profile like this, right? But we need not know the probability values at every point of this probability distribution. The mean value and the standard deviation is sufficient to define the entire Gaussian distribution. So the mean and standard deviation can be considered as the sufficient statistics for a Gaussian distribution. In the same way, a Markov state can be considered as a sufficient statistic for the entire future. So any sequence of states or observations and actions and rewards that we can expect in the future can be modeled only given the current state ST. So we don't require the entire history to take any future actions, right? Now, the environment state, where we know everything about the environment, or the complete history, both of them can be considered as Markov states because they have all the information required to take the next action or for the environment to update its next observation and reward. So all the algorithms that we will see throughout this course, right, have this one assumption that we will always use a state assumption which is Markov in nature, right? There can be exceptions to this. There are many use cases where there are exceptions to this, but we work under this assumption and derive approximate solutions. Now, we can have environments that are fully observable and we can have environments which are partially observable. So if we think about board games like chess or Ludo or like Go, right? So these board games can be considered as fully observable environments because if we know the current sequence of the coins on the board, that explains all the information about the current state of the game, and we need not know any of the previous transitions. So board games are typically fully observable. So what the agent observes or sees as the current state of the board is the same as the environment state, is the same as the agent state, and it follows the Markov property. So wherever we have fully observable environments, we can define something called a Markov decision process, which defines the formulation where we can design RL algorithms, right? On the flip side, we can also have partially observable environments. So if we are talking about a full humanoid robot which is walking in an environment, this is a very typical example of a partially observable environment, right? So in this particular case, it is very difficult for us to know what are the forces that the robot is feeling and what is the wind that is blowing on the robot and any other forces that are applying on the robot, right? So the agent may not have good enough sensors to accurately measure all the forces that are falling on the robot, right? And the agent can only have a partial observation. So whenever we have a partially observable environment, we define something called a partially observable Markov decision process. So this idea of an MDP and a POMDP, we will be covering in the later videos of this course. So wherever we have a partially observable environment, the agent is required to construct some representation of the state, which is enough for it to solve the task, right? So this is the approximation part that I was talking about. Now, the naive thing that we can do is that the agent can consider the entire history to take its next action, right? Or in some studies, we can use something like a recurrent neural network, an LSTM or a RNN network, where the current observation and the previous state are provided as inputs. So some estimation of the previous state, agent state, and the current observation can be combined to output the next state. So there is always some information that is encoded about the history inside the agent state, right? Or we can also if we can divide the entire state space into certain discrete set of states, then we can also maintain some probability distribution where at every time step we have some probability distribution saying in which state the agent might actually be in, right? And different state representations that we use can result in different types of RL algorithms. So with this, I conclude the content of this video. And here we covered a more in-depth understanding of what we mean by the reward, action, and the state. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.